Okay, so this is the lecture on for physical science on work and energy, just sort of the overview of these physical properties, and then it's chapter 6, I believe, in your book. First, let's look at work. If we've got some sort of a movement happening, an acceleration or a velocity, we know that the velocity will tend to stay the same, but any speeding up or slowing down is caused by a force. Still, even though we have forces working on things, if we take the force and we multiply it by the distance over which the force occurs, we have a particular property which we call work. Okay, work is very good. It represents a way in which things get moved around, pushing things over by a force over a distance, but it fundamentally has a different property as well. It is a conserved property of nature. Once some work has been done, it always is. It never disappears. It can be stored or it can be used in a different form. Okay, let's take an example of where we might use work or how we might calculate it. Let's suppose I take a 1 kilogram book, I raise it up 1 meter, and I want to know the work that I did on the book, and the answer is that I put a certain force on that book. Force is mass times acceleration. If it's the acceleration due to gravity and the mass when I'm doing something against gravity, then it'll be this m times g. So let's do that. Let's do the force. The force is going to be 1 kilogram times the acceleration due to gravity, 9.8 meters per second squared. That'll be equal to 9.8 kilograms meters per second squared. And we had previously called this the Newton. That'll be equal to 9.8 newtons. Okay, very good. So we'll get 9.8 newtons. Now the property of work we'll get by taking this force times how far we move something against a force. So 9.8 newtons times 1 meter gives us 9.8 newton meters. So we have a new unit to worry about. Work is going to be in units of newton meters, and then we generally have a name for this. We are going to call it a joule. So 9.8 joules is the amount of work we did. So joules from now on will represent a unit of work, the SI unit of work. Now the bottom part here, a change in energy causes work, represents the fact that if we do some kind of work on something and the work gets stored, like it can come back out, we're going to call that energy. Energy is what gets used to cause work to happen. Okay. Now another aspect of work that's worth talking about right up front is something called power. Okay, and we have power used all over in our daily lives, but from a physics point of view, it's how fast work is done, and that's the work divided by time. So let's say I do this thing again, I raise, and let's not do a 1 pound, let's say kilogram again. I don't know why I put pounds in there. Let's say I've got a 1 kilogram book and I raise it up 1 meter, but this time I'm going to worry about time. I do it in 1 second. Very good. Well, now I want to know the work, the newton meters. We went through some trouble to show that the newtons were 9.8 newtons of force over 1 meter, so that'll give us the number of joules, but now we're going to divide it by 1 second, and we're going to end up, I did an easy math version here, we're going to end up with 9.8. Now we've got newton meters or joules, but we've got joules per second. And you've heard this term before. We'll actually use it again. When you hear the units of watts or capital W, it's going to be a unit of power. It's always going to be the work, and we'll talk about energy in joules too, the work or energy per second. One of the more familiar things is like a light bulb that might be a 60-watt light bulb. Of course, this is very important because if you have a 60-watt light bulb, it's going to be brighter than a 30-watt light bulb because it's using more energy per unit time, per second, more joules. Okay, work and energy. Let's get into that. All right. So energy is going to be defined as something that causes work to occur. Okay, and in mechanical energy is just energy you can kind of see with something you can hold in your hand or push around. But there are some other types of energy that are less easy to hold. But we'll do mechanical energy. So work to occur, let's say I raise that, that book up and it's in the air, but if I let go of the book, it's going to come crashing back down, so the work's being done on the book, force over distance. And so when it's sitting up in the air, we're going to call that potential energy. Potential energy is something that is sitting there waiting to do some work on something, but it hasn't happened. Kinetic energy is going to be the actual energy of motion. So let's suppose we allow the book to fall. Once you see something speeding up and moving, we're going to say that's a form of energy, and we're going to call it kinetic. So potential energy is the energy of position, and kinetic energy is the energy of motion. And any type of energy is something that can cause this property of work, moving something against a force to occur. Now I've got the mathematical equations here for potential energy and kinetic energy, and they're fun to do problems with, but I've decided in this course that we are going to not do the calculations on some aspects of things, and this is one that we're not going to do. Here are some nice examples of where you can see potential and kinetic energy being stored. If you pull back a bow and arrow, pull back a spring, stretch out a rubber band, or raise a book, they're all just sitting there waiting to release some sort of work on something or to give some kinetic energy to something. And so these all represent things that have potential energy. And then if you let go of the bow and arrow, the arrow shoots off. It goes to kinetic energy. A spring will spring back up. A rubber band will fly across a room. A falling object will fall if you let it fall. And so not only do we have energy stored in these objects as energy of position, potential energy, but they can be released as kinetic energy, and probably more important than anything is that one type of energy can go into the other type of energy. That is, when you release the bow and arrow, the potential energy gets completely released, but it all goes into the arrow. Okay, here's a slide that does a little bit of an exercise on a car crash, and it's kind of interesting, but over the semesters I've decided not to put this into tests and homework. I think I'm going to skip this, this aspect of energy and move on to the next one. Okay, this is conservation of energy is an idea that I'd like you to be able to have at least as an idea about the way the world works. It's stated energy cannot be created or destroyed, only changed from one form into another. Okay, we'll take the example of a pendulum because it's a closed system, meaning that the energy doesn't get in and out, and there are only two types of energy. And so we can see how energy gets conserved in a closed system with only two types of energy. What we do, and we didn't do this this semester, but often in the lab, is we'll have something set up like a ring stand that has a little ball hanging on the end, and we'll look at the two forms of energy. One form of energy is when you raise the ball up, you give it potential energy because it's sitting there waiting to come back down. And then if you release it, it'll swing back down and it'll have a lot of motion, and at the very bottom it'll have the most motion, so it will have kinetic energy at the very bottom. Okay? And as the ball goes up to the highest point again, it will stop. So the kinetic energy is actually zero at the top, and then it's the maximum at the bottom. And when the kinetic energy is zero, the potential energy is the greatest. So we see that all the kinetic energy has been transferred to potential energy. Now when the ball comes all the way down to the bottom, its energy of being raised is completely gone because it's gone as far down as it can. So there the potential energy is zero, and it's be transferred all the way over to kinetic energy. So as the ball swings back and forth, we can see the energy is conserved because it swings to the same height each direction, giving you the same potential energy each time, and it swings through the bottom with the same speed each time. So when the energy goes to kinetic, it's still saved as the same amount of kinetic energy. Very good. Now, other things that are important to us, I'm going to point out right here. If energy is conserved, the potential energy putting the ball up goes to a certain height, and when it swings the other direction, it goes to the same height. And if the kinetic energy, when the energy all goes to kinetic, is conserved, why does the ball ever stop? The energy should be just going back and forth from one part to the other. And the answer is the transfer of energy from one form into another is never 100% efficient. So some of it will always get away. The energy will never be destroyed. It'll always be there, but it's never 100% efficient. In the case of the ball, it's probably mainly the friction of the air on the ball. What will happen is that if you were to measure the temperature of the ball's surface, you would probably find it increasing as the air rubbed against it. And that energy of heat is drawing off the energy from potential when it's at the top and kinetic when it's at the bottom. Okay, now the last point is getting away from the pendulum, this closed system, and that is energy can be transformed, but there are many different types of energy. And I guess I'd like you to be familiar with the different types of energy, and I'm going to list them. In class, I usually have you guys kind of figure them out, but in this situation, I'll have to list them. First of all, types of kinetic energy. My pen won't work. Kinetic energy. Types of kinetic, there it is, kinetic energy are familiar things to you. They're light, sound, electricity. Light, sound, electricity, heat. Okay. There are lots of forms of potential energy, and we will be concerned with not just the gravitational one, but also two that are very important in our lives. Any type of food, because the food is sitting there doing nothing, but then when we eat it, it gives us energy, so it's potential. And fuel. So fuel can sit there and do nothing, but when you put it in your car, it gets it to move. So the fuel is just a storage form of energy, and it's not kinetic. Okay, getting down to the bottom part here again, energy can be transformed between all these different things, and if you pick something out, let's pick the car motion, you'll find an interesting property of all the energy in our life. So the energy of movement of a car comes from the gasoline. But where does the gasoline come from? Well, it came from oil that is in the ground. Where did the energy in the oil come from? Well, it turns out that oil is just a crushed down plant matter that's been crushed down for so many millions of years it's transformed into oil. But where did the plants actually get the energy from to make the oil? And the answer is the plants got the energy from the sun. Now, without spending a lot more time, I just don't have it in this presentation, I'll say the motion of cars' energy ultimately came from the sun, and you could look at the energy of life, the energy of falling rain, the energy of a TV set, you pick it, the energy of everything can be traced back to transformations between all these different forms of energy, right back to sunlight. So an interesting property of our world is all energy comes from the sun. Okay, so those are the main points. for work and energy, and so that's good enough for chapter 6.